What if the future of flight didn't creep forward step by step, but took a bold, electrified leap overnight? Imagine an aircraft designed like a Tesla, sleek and intelligent, priced more like a high-end gadget than a multi-million-dollar jet. That's the disruptive vision behind the Tesla super electric plane. A promise of quiet, fast, low-cost air travel that challenges everything we think we know about aviation. But the question remains, is this truly the beginning of a practical electric aviation era, or just another ambitious concept racing ahead of science, certification, and physics itself? This question matters for more than just engineers and airline executives. It could reshape the travel experience for every passenger, redefine airport operations, and redraw the skylines we see from above. The world of flight may soon be as silent, efficient, and connected as the Tesla cars on our roads, but reaching that vision means untangling both innovation and hype. Picture a minimalist fuselage gliding effortlessly through dawn skies. Its surface smooth, like polished glass, its engine silent but powerful. The landing gear tucks away seamlessly, wings flex and reshape themselves mid-air, and hundreds of tiny electric motors hum in perfect synchronization. Beneath the body, a battery module slides out like a cartridge, ready to be replaced within minutes. Inside, the cockpit glows with advanced predictive displays, giving pilots a sense, almost like intuition, the ability to anticipate conditions before they unfold. And now, imagine all this with a price tag closer to that of a compact car than a luxury jet. Suddenly, the concept of personal or small-scale air travel feels accessible, not extravagant. More people could own, rent, or operate electric planes for regional flights, connecting cities in ways today's infrastructure barely allows. It's an intoxicating idea, one that blends the clean futurism of Tesla, designed with aviation's age-old dream of affordable flight, but bold promises demand close inspection. When a company claims 400 miles of range, 12-minute battery swaps, and drastic cuts in operational cost, those aren't just specifications. They're statements that shake industries built on decades of predictable regulations, heavy infrastructure, and slow certification cycles. Our goal isn't just to marvel at the ambition, it's to separate what's possible today from what remains experimental or purely theoretical. Tesla's strategy here isn't entirely new. It's an evolution of what worked on the ground. Take the same manufacturing discipline that revolutionized cars, the scalable Gigafactory model, modular assembly, and standardized testing, and apply it to the air. That's how Tesla envisions transforming aircraft production from slow, handcrafted assembly lines into something closer to consumer electronics manufacturing. Instead of individually built fuselages and riveted panels, imagine prefabricated components, wings, fuselages, battery modules, and motor pods arriving at the factory as pre-tested modules. Each one is tracked by serial number, assembled in hours, not weeks. This modular design reduces defects, shortens production cycles, and allows mass scalability. Aircraft that once took months to construct could roll off the line in days. The materials would change too. Large composite panels would replace traditional aluminum skins, bonded together with precision joints instead of thousands of rivets. These lightweight materials not only save mass, but also enhance aerodynamics. Inspections could be done by simply swapping out modules rather than tearing down the structure for hours. The benefit isn't cosmetic, it's about uptime. In aviation, every minute a plane sits idle on the ground is lost revenue. Where Tesla truly meets aviation head-on is in powertrain, design, and energy management. Electric motors are inherently more efficient than combustion engines, converting a higher percentage of stored energy into thrust while running quieter and with fewer moving parts. Maintenance demands drop dramatically because electric systems don't require complex fuel lines, exhausts, or gearboxes. Even more revolutionary is the concept of distributed electric propulsion, dozens of small motors placed along the wings instead of one or two massive turbines. This arrangement allows the airflow over the wing to be precisely controlled, increasing lift at lower speeds and enabling shorter takeoffs. It also provides redundancy if one motor fails. Others can adjust seamlessly to maintain stability and thrust. This efficiency also unlocks new aerodynamic possibilities. Instead of building for brute force, aircraft can be designed for elegance. Long, slender wings, smooth composite skins, and sealed joints that minimize drag. Every detail from retractable landing gear to nano-coated surfaces is optimized to reduce resistance. Each saved watt translates directly into more range, however. Even with these advancements, there's an unavoidable truth. Batteries are still heavier and less energy-dense than jet fuel. This is the single greatest constraint for electric aviation. Every kilogram saved in structure or system weight is critical, which is why Tesla's engineers push for extreme aerodynamic efficiency and lightweight construction. That's also why some of Tesla's most eye-catching claims require skepticism. Numbers like 347% efficiency improvements or 127 kilowatts recovered during descent sound spectacular, but they often represent best-case simulations, not certified real-world tests. Regenerative energy capture during descent is real. When propellers windmill during a glide, they can act like generators, reclaiming kinetic energy. But the actual amount recovered depends on variables like aircraft speed, propeller design, and atmospheric drag. Tesla's genius has always been in integrating systems, not in defying physical limits. They achieve breakthroughs by combining small, realistic improvements across multiple domains, materials, software, aerodynamics, and manufacturing until the combined result feels revolutionary. It's not one big leap, but 1,000 small optimizations adding up to something that changes the game. Take the battery cassette system. For instance, instead of charging the plane directly, Tesla envisions pre-charged battery packs waiting on the ground. When the aircraft lands, a robotic system could slide out the depleted module and replace it with a full one in under 12 minutes. This concept removes charging time from the equation entirely, allowing planes to operate continuously throughout the day, of course. This isn't just a mechanical challenge, it's a logistical one. Airports would need to maintain inventories of charged cassettes, train technicians, and build infrastructure for high-speed depot charging. Tesla's approach is to treat aircraft turnaround not as a slow refueling process, but as an orchestrated, automated routine, an industrial ballet of precision. Much like its car factories, the modular motor pods themselves could revolutionize maintenance. Each pod would contain its own sensors, health monitoring systems, and quick-release connectors. If one fails, it can be replaced in minutes instead of grounding the plane for days. This approach mirrors how data centers swap servers or how Tesla cars receive over-the-air updates. The more digital and modular the aircraft, the less downtime it endures. But complexity also brings new challenges. Managing dozens of electric motors, high-voltage systems, and liquid cooling loops requires robust engineering to prevent electromagnetic interference, thermal overload, and voltage spikes. Aviation certification authorities will demand extraordinary levels of reliability, documentation, and testing before such systems are cleared for public use. Even the aircraft's exterior design carries layers of engineering intent. Skin friction, the invisible drag that forms when air slides across the body, is one of the biggest enemies of electric range. Tesla's use of smooth one-piece composites, flush inlets, sealed joints, and nano-coated surfaces is meant to minimize that. The high aspect ratio wings and winglets further reduce induced drag, letting the plane glide farther on less energy. Every small design decision has a ripple effect on efficiency. Details like recessed door handles, integrated sensors, and aerodynamic LED lighting are not just aesthetic touches. They're functional, energy-saving refinements. Inside the cabin, Tesla's minimalist philosophy continues. Instead of cluttered panels of switches and dials, pilots would control most systems through a single, intuitive display backed up by dedicated tactile controls for critical functions. This design shortens training time and reduces cognitive load, crucial when the same aircraft might perform multiple short flights in a single day. Comfort is also strategic. Quieter motors mean a calm cabin, and better ergonomics reduce pilot fatigue during high-frequency operations. Adjustable seating, clear sight lines, and climate-controlled airflow preserve alertness and precision. Thermal management, both for passengers and batteries, is handled by smart heat pumps and liquid cooling systems, which minimize power drain while keeping temperatures balanced. Tesla's approach to aircraft software is perhaps its most underestimated strength. By using over-the-air updates, Tesla can continuously improve performance, efficiency, and safety features without grounding planes for maintenance. It's the same strategy that transformed its cars into constantly evolving machines. Then there's the more speculative side, ideas that border on science fiction, like neural command interfaces or predictive AI copilots. The idea that a pilot could control flight systems with subtle neural input, or that AI could anticipate human intentions before commands are given, is deeply. Brain-machine interfaces are being